So let me start explaining this very long title. So this is a joint work with Omri Ben Eliezer, who is now in Harvard, and Dan Chefetz from Ariel University, and Michael, who was just here. So what is a semi-random process? What do we mean by that? So we mean that there is some random environment, but there is a player who can make intelligent decisions, and somehow there is an interplay between these two things. So let me show you a maybe famous example that is not related directly to what we are doing, but still it's nice to see it. So this is due to Azar et al. So here the game is as follows. So suppose we want to distribute n balls into n bins, and our goal is to keep all the bins, the load of each bin to a minimum. So we want that the bin with the maximum number of balls will be as small as possible. So suppose first that we do it randomly. So each time a ball comes, we just choose one of the bins at random. Then it turns out that the number of balls in the fullest bin will be roughly log n over log n with high probability. Okay. Now suppose that we are given some ability to make decisions, namely that now for each ball, there are two possible choices, two possible bins which are given to us at random, and we can choose one of them and put the ball in that bin. Okay. So it turns out that with this very naive, very limited maybe power, we can already do much better. So we use a very simple strategy. We just put a ball in the bin which is less full at the moment. And even by doing this very naive thing, we already reduce the fullest bin to log n with high probability. So we see that there is a lot of power that even in a randomized environment, there is a lot of power to making intelligent decisions. And another example of a similar flavor now for graphs is the so-called Achlioptes process, where at each step a player is given two random edges. It has to select one of them. So I will not go into detail about this because this is not the topic. But if you know this, then okay. So I will actually discuss a different type of a semi-random process for graphs, where instead of being given random edges, we will be given random vertices. So the goal of this game is to make the graph satisfy some increasing graph property. So for example, to make the graph have minimum degree at least 100, say, or to construct a triangle, or to construct a Hamilton cycle, and so on. And the question we will be asking is, if we play optimally, how many rounds does it take on average or typically to achieve this goal? And we also ask, what is the strategy that guarantees this thing? Okay. So let me just say that this model was introduced by Peleg Michaeli. So let me give you an example of how this works. So at a given point, we are offered this vertex, for example, and then we select an edge which touches it, like so. Then we are offered another vertex, and we select another edge, and so on. And suppose we want to construct a triangle. So when we're offered this vertex, we can already close a triangle, right? And we are done. Okay, good. So it turns out, so this process was introduced fairly recently, and already there are some works about it, and it seems that there are some interesting open questions, which I'll mention later. So the first paper on this model was by this group: Ben Eliezer, Chefetz, Cronenberg, Parchik, Schichelman, and Stojakovic. And let me tell you some of the results which they proved. So, for example, they considered the problem of constructing a copy of a small graph H. And they showed that if H is D-degenerate, then this can be achieved in time n to the 1 minus 1 over d. So in particular, it's sublinear time. And if H is a clique of size d plus 1, which is also d degenerate, then this bound is tight. Another result which they had is that if our goal is to achieve minimum degree k, then, well, if you want minimum degree k, you need at least kn over 2 edges. And they showed that this is, in a sense, tight, that you can achieve this with a little bit more rounds. And in fact, you can even achieve k connectivity with this number of rounds. And they also considered the problem of constructing a Hamilton cycle, and they showed that this can be done in linear time. So given all these results, it makes sense to ask about additional structures, and Noga alone indeed asked what happens if we want to construct a triangle factor. And so the question is, can we construct a triangle factor in time linear in n? So here is a triangle factor, it's just a union of n over 3 disjoint triangle. So here is, I'm sorry. So the question, so this is a mistake. The question is, can we do it in time O of n? And our main result is that, in fact, we can. And not only that, we can do the same for every spanning graph which has bounded degree. So here is the theorem precisely. So if we have some spanning graph H of maximum degree delta, so H can be a triangle factor or a Hamilton cycle or any other spanning graph of maximum degree delta, then there is a strategy to construct H which works in time that is linear in n. And in fact, even the dependence on delta is only linear. It's rather modest. So you see that we can do it in roughly 3 delta over 2 times n rounds. And this is almost optimal. So in what sense? So of course, if we want a graph which is delta regular, for example, then of course we didn't need delta n over 2 edges, and here the number of rounds which we use is only a 3-factor away from this number. Okay, and here again we can compare this result with what happens in the purely random setting. So if all choices are made at random, then this is just the random graph process. And then we know that even to get a single copy of a clique of size delta plus 1, we need much larger number of rounds. So n to the 2 minus 2 over delta. While here, in the semi-random setting, we can do it in linear time. OK, so this is our main result. And as we said, this is tight if the average degree is also of the order delta. And now we can ask what happens if the average degree is much smaller. So can we do better? And it turns out that we can if our graph is a forest. So another result is that if we have a forest, a spanning forest of maximum degree delta, then we can construct it in time only log delta times n. And this is, again, optimal if we consider the forest to be a union of stars. OK. And let me mention that the analogous statement for d-degenerate graphs is still open. So so forest is 1 degenerate, but if you take d-degenerate for larger d, then this is not known. OK. So let me say something about the proof. And let me focus about the case of a triangle factor. And so our goal is to show that the triangle factor can be constructed in a linear time with high probability. So it turns out that, well, using a trivial strategy, which I'll explain in a moment, we can embed almost all of the triangles. So we need to embed n over 3 triangles, disjoint triangles. And using a very trivial strategy, we can embed almost all of them, even if we decide what the triangles are going to be in advance. So, of course, we don't have to do this, right? We can run the process and only later decide what triangles constitute our factor. But even if we decide which are the triangles in advance, we can still embed almost all of them. So how do we do it? We simply, those are the triangles that we're trying to achieve. They have no edges at the beginning. And every time we sample a vertex, we just connect it to one of its neighbors in the triangle that we want to get. So you can imagine we do it for a long time, and these triangles fill up. And in fact, after a linear number of steps, almost all of these triangles will indeed be triangles. So almost all of them will indeed succeed in putting all three edges. So why is this true? Okay, so in order to complete a triangle, we only need to see all of its vertices. So we only need that each of the vertices is offered at some point. Because we can assign to every vertex one of the edges of the triangle, and when this vertex is offered, we select this edge. So what is the probability that a vertex is not offered at all? So if we run this process for c times n rounds, where c is some large constant, then the probability is roughly e to the minus c. And therefore, all but this small fraction of triangles will be present in our graph. So this is good news. The bad news is that it's not clear what to do with the remaining vertices, right? With the remaining triangles. So a naive approach, a naive attempt will be to just wait, to do the same thing we did just now, just wait until they are offered and connect the vertices inside the triangle. The problem is that in order to see all vertices, we need n times log n rounds, right? This is just the coupon collector problem. So this is not good enough. So we have to do something more clever. And indeed, what we'll do is something which we call role switching. So let me tell you, so this is somehow the heart of the argument. This is this role switching. So let me tell you what it is. Okay. So suppose we are in the following situation. So we have successfully embedded all triangles but one, this triangle XYZ. And now we're trying to make it also a triangle, this XYZ. And say we are only missing one edge, the edge between X and Y. So we do not want to wait until X or Y is offered. This will take too long. But what we can do is we will try to use one of the vertices AI to somehow replace X. So I will explain how it works now, and it will be clear, I hope. So what do we want to do? So in order to replace, say, A1 and X, what we want is that we want to connect A1 to Y and Z, so that A1 will form a triangle with Y and Z. And we need to connect X to the other two vertices in the triangle T1, right? Because if we manage to do this, then Y, Z, and A1 will be one triangle, and X with the remaining two vertices in T1 will be another triangle, and then we will be done. So we think about it as replacing the roles of X and A1. So now X is assigned to this triangle and A1 to the triangle T1, and we want to switch it. So now we try to do it. So say we sample A1, then we connect it, for example, to Z, and then we sample a vertex. You see, all the vertices, A1, A2, and so on, they try to do this role switching at the same time. So we cannot guarantee that one of them will succeed with high probability, that a specific one will succeed with high probability. But what we can guarantee that at least one of them will succeed with high probability. So now, for example, we sample something in the triangle T3, then we connect it to X, right? Because we want to switch X and A3, and so on. We connect A3 to Z, and then this vertex is offered, so we connect it to X as well. And finally, A3 is offered, and we connect it to Y, and now we are done. So we see that A3 is connected to Y and Z, and X is connected to the other two vertices in T3, and we've successfully switched X and A3. So this is somehow the basic idea. And what's good about it is that we never have to see X, Y, or Z in order to fix this triangle, right? We only have to see the vertices from these triangles Ti. And essentially, it's only about the numbers. So if we have a lot of these AI, if K is large, then it's very likely that one of the AIs will succeed. Okay, so let us look at a slightly more complicated situation. Suppose now that we don't have any edges between X, Y, and Z, but still we want to fix this triangle. So now it's not enough to switch X with some AI, right? Because we still will not have the edge between Y and Z. So now we need to do two switchings. So we will try to switch X with one of the vertices, and we'll also try to switch Y with one of the vertices. So A1 up to AK will try to switch with X, and the B1 up to BK will try to switch with Y. Okay. So we run the same thing, right? Suppose we're offered this vertex, we have to connect it to X because we want to switch AK and X. So we connect it to X, that's good. We are offered this vertex, we connect it to X as well. Now suppose we're offered B1, well, B1 tries to switch with Y, right? So we need to connect it to the neighbors of Y, so to X and Z. So let's say we connect it to X. And now maybe we're offered the AK and we connect it to Z, and we're offered it again and we connect it to Y. And now AK is already in good shape, right? AK is connected to both Y and Z, which are the intended neighbors of X. And X is connected to both neighbors of AK. So now we already do the switch. So what I'm trying to demonstrate here is that the switching happens on the fly. So as soon as we're able to do it, we already switch. And now let's look again at B1. So we see B1 tries to switch with Y, and therefore we connected B1 to X. But now X was already switched. So now the new neighbors of Y are not X and Z, they're AK and Z. So now this edge between B1 and X is useless to us. So let's ignore it. And we continue. So we're offered B1 again. So we connect it to AK now and say we're offered this vertex. Okay, we connect it to Y and this vertex to Y as well. And then we're offered B1 again. We connect it to Z. And now B1 is also in good shape. So it's connected to the neighbors of Y. And Y is connected to its neighbors. So we can switch them. And maybe it's a bit hard to see in this picture, but we really have now 3 triangles. And we are done, right? We have our triangle factor. So let's try to a little bit analyze when this goes well. So what do we need in order to guarantee that Y is really switched? Well, if we think about it a little bit, it turns out that if every one of the neighbors of BI, say B1, is offered, and after that, BI itself is offered at least 3 times, then BI will successfully switch with Y. Why we need 3 times? Because we saw this, that some edges might go to waste, right? Because we connected B1 to X, but then we switched X and we had to connect to someone else. But if it's not hard to convince ourselves that if BI is offered 3 times, then we're good. Okay. So now let's just work out the numbers. So suppose that at some point we have only alpha n bad vertices, and let's think of alpha as some very small number, but constant. Okay. Now what we do to each bad vertex, to each vertex we want to switch, we assign to it 1 over alpha candidates, right? Because we have n vertices, alpha n bad ones. So roughly we can assign to each bad one alpha 1 over alpha good ones. And then the strategy is that all of these candidates try to do this role switching simultaneously. And then it's not hard to show that after, say, alpha to the 0.1 times n rounds, and this 0.1 is kind of arbitrary, I mean, just need to be some small enough number, all but exponentially a small number of bad vertices were switched. So they became good. So now we don't have to worry about them anymore. So we started with alpha and bad vertices, and after this role switching thing, we're left with substantially fewer, so exponentially fewer bad vertices. So this is a good situation, right? So how does one prove this? Well, remember that in order to switch for BI for example, in the last slide to switch, we just need to be offered the 2 neighbors of BI and then be offered BI at least 3 times. So we just have at 5 different rounds to be offered the right vertices. So the probability is roughly what is written here. And then we use some, so this is the probability for a particular vertex to succeed, but we have 1 over alpha candidates. So we see that we have alpha to the minus 0.5, so quite a large number of successful candidates on average, and then we have to use some concentration inequalities. So now we can describe the general strategy for embedding a triangle factor. So first, we use some this trivial strategy where we fix the triangles to embed almost everything. So this is step one. And then we iteratively, in phases, we run this role switching. So at the beginning, we have alpha 0 times n bad vertices. Then we run this thing. Now we have only exponential in alpha 0 times n bad vertices, and so on. And the total number of rounds is only, so we see that these fractions alpha I, they go to 0 very, very quickly, like a tower, right? And therefore, a tower of exponents, and therefore the total number of rounds is only linear. Okay. So now let me end with some open problems. So one open problem is to improve our result to an optimal one, right? So we showed that if you want to embed a spanning graph with maximum degree delta, then you can do it in roughly 3 delta over 2 times n rounds with high probability. And the lower bound, which is trivial, is delta n over 2, because you need this number of edges at least. And it's interesting to decide if you can really do it optimally. So if it's really possible to do in delta n over 2 plus some small error rounds. And another question is what happens for specific structures. So, if you consider a perfect matching or a Hamilton cycle or a clique factor. So an interesting question is whether we can prove really tight bounds. So whether we can find a constant, alpha say, so that to construct a Hamilton cycle, we can do it in alpha n rounds, but we cannot do it in alpha n minus little of n rounds. And the last question, which I already mentioned, is to construct D-degenerate spanning graphs of given maximum degree. So as I told you, we know how to do this for forests. So this is the case D equals 1, but we do not know for any larger D. Okay, so let me stop here and thank you.
Let's thank our speaker. We might have time just for 1 or 2 quick questions. And by the way, during your talk, there were some questions in the chat, but it's fine. It turned out that our chat is a self-managing structure, and got multiple answers from different persons. So it's very good. But you do from Rupik Sue about geometric version.
Yeah, so I see there is a version. So I actually do not know about this, I have to say. So yes, so I have to say I'm not aware of this. So I have to maybe we can talk somehow after the talk. Yeah, I'm not aware of this work.
I have a question, but unfortunately we don't have time. I'll write you in privately in chat.
Okay.